all of our members.
Yes, good group. So thank you. So we take this time to acknowledge the lands we all stand on today, have been called home by the indigenous peoples of the Salish Sea since time immemorial. We recognize tribal sovereignty and that this place holds special spiritual, cultural, and personal significance for Indian tribes and First Nations. And we acknowledge our responsibility to lift the voices of our tribal brothers and sisters in our life and to work to find justice and belonging in all we do. Thank you very much. So let's go ahead and get started here, and just won't spend much time, just turn it over to David to tell us everything that we need to know about ESA.
So we're going to tag team this. Amber and I are going to tag team an ESA introduction talk and Puget Sound recovery talk into a 15-minute overview, essentially. So expect a wake here. I think I'll go pretty fast and probably touch on some of the highlights of the Endangered Species Act. Okay, so the first thing about the Endangered Species Act you should know is that it was conceived in 1973 under then President Richard Nixon, who is arguably one of the greatest conservation presidents of the US. And I say arguably because you can draw your own conclusions, but the Marine Mammal Protection Act, Endangered Species Act, Clean Water Act, Clean Air Act all came under his tenure. So one of the purposes behind the Endangered Species Act is conservation. In fact, I would argue that's first and foremost the purpose behind the Endangered Species Act. It's not often what we think of, and I'll get into that in a few minutes, but conservation is what this program essentially was designed to do. And it was designed from an ecosystem perspective. So early in the concept of ecosystems for the recovery of threatened and endangered species. The Endangered Species Act is administered by two federal agencies. One is NOAA, of course, and we have about 165 species under our current listings. And U.S. Fish and Wildlife Service has over 2,000. So just to give you some perspective there. This is a West Coast wide view of marine species listed under the Endangered Species Act. You see Puget Sound right up there in the upper corner. We have 28 salmonids listed throughout the West Coast region, and 9 whales, 5 sea turtles, scattering of rockfish, sharks, and some invertebrates. One important concept here is when we say species, we designate species along an evolutionary significant unit line. That is, Chinook salmon in the Puget Sound is different than a coastal California Chinook salmon, and they are listed individually as species along that subspecies line. So not just like Chinook everywhere, but Chinook along these important evolutionary distinct units. So with the Endangered Species Act, here are a few highlighted sections that I'm going to breeze through. Purpose and policy, definitions briefly. Section 4, which is relatively meaty. I'm not going to talk much about Section 6, which includes cooperation with states. Talk a little bit about prohibitive acts under Section 9. I won't touch on the exemptions under Section 10, which include research permits and habitat conservation plans. Penalties and enforcements, unfortunately, are one of those things I know the least about with respect to ESA, and therefore won't be covering it. Marine Mammal Protection Act, I won't touch on that unless there are questions, and that's in Section 17. Despite the fact that we think of the ESA as a conservation organization, and Section 7 there in the middle does include an important provision for conservation. We spend a lot of our time in the regulatory portion of Section 7. I'll talk a bit about that in a second. So it is a policy of under the ESA under Section 2 that all federal departments and agencies seek to conserve endangered species and threatened species and to use their authorities to advance the act. So that means not just avoiding the ESA or minimizing harm. It is to actually proactively conserve threatened and endangered species with their authorities. And what does conserve mean? It means to use all methods and procedures necessary to advance the act, which is, of course, to see the species recovered. So not just a regulatory hurdle, it is an active program designed to conserve endangered species and bring them back to recovered status. Section 4 includes a great deal, listing and recovery, as well as some other provisions, some exemptions from take. So the Section 4 prescribes specific determination processes that both U.S. Fish and Wildlife Service and NOAA must follow in order to list a species and to designate its critical habitat. As you guys know, there are endangered species, which means imminent danger of extinction throughout all or a significant portion of its range. Threatened species, of course, means likely to become endangered in the near future. And critical habitat includes specific geographic and areas with physical and biological features that are necessary for the conservation of the species. I'll talk a bit about critical habitat here in a second. So there are 5 listing factors when a species is listed, and you'll also see these 5 listing factors in every 5 years under what we call a 5-year status review. And these include the present or threatened destruction or modification or curtailment of habitat, overutilization, which includes commercial, recreation, scientific, and educational exploitation, disease and predation. You might hear a little bit more about sunflower sea star with mass wasting disease, taking that species from healthy to almost non-existent. Number 4 is the inadequacy of existing regulatory mechanisms. That's an important one. And 5 is natural or other man-made factors that affect the continued existence. Examples of this might include hatcheries, for example, or climate change. Okay, what is designated critical habitat? Critical habitat must be designated after an ESA listing. And the ESA prohibits the destruction or adverse modification of critical habitat. Critical habitat is typically occupied by the species at the time it was listed and contains physical or biological features that are essential to the conservation of the species. And they may require special management considerations or protections, especially in highly sensitive areas. I have no examples of this, but critical habitat may also include areas that are not occupied by the species at the time of listing, but are essential for conservation. Things like that might include, conceivably, areas above blockages where the species is currently blocked, but the habitat may be necessary for recovery. Okay, despite the fact that ESA is first and foremost a conservation program, we at NOAA spend a great deal of our time administering 7A2, which is a regulatory section of the Endangered Species Act. Under Section 7A2, first of all, 7A1, federal agencies are required to help conserve species using voluntary and cooperative methods. But 7A2 requires that federal agencies consult with the services being U.S. Fish and Wildlife Service or NOAA, for any activities that could possibly injure listed species. And those activities include the authorization, the funding, or the actual carrying out of activities, in whole or in part, to prevent the listing of, or to prevent the jeopardizing, to prevent jeopardizing listed species or modify or adversely modifying their critical habitat. So that what that means is essentially if U.S. Fish or U.S. Forest Service wanted to issue a contract to do work that could impact listed species, the U.S. Forest Service would have to consult with NOAA on those activities. If the Department of Defense wanted to build a wharf or something in that may cause some impacts to listed species, they must consult with NOAA. If FEMA wanted to issue a grant to a local government, and that activity may lead to impacting listed species, FEMA must consult with the services. So under Section 9 of the ESA, there are 5 take provisions. The one that matters most is the 5th one, which is take within the US. And take is defined as harass, harm, pursue, hunt, shoot, wound, kill, trap, capture, or collect, or attempt to engage in any of those activities. Now, those are pretty straightforward, except harass and harm, which have been interpreted by the services under policy guidance as an activity which actually kills or injures fish, could include significant modification or degradation of habitat that actually kills or injures fish, or significantly alters behavior patterns, such as rearing habitat, spawning habitat, feeding and sheltering. Harass is a little more vague, but it requires the likelihood of injury to wildlife by significantly disrupting its behavior patterns, including breeding, feeding, and sheltering. ESA consultation processes seems pretty simple looking at this graph, but can be complex. First of all, the action agencies must determine whether or not there's an effect on listed fish. If there is no effect, NOAA hears almost nothing about it. If an action agency determines that their actions or their associated activities may affect a listed species, then they must determine whether or not it is likely to adversely affect, which would be or not likely to adversely affect, which includes insignificant, discountable, or completely beneficial activities, versus likely to adversely affect, which could actually harm listed species. So in the event of a not likely to adversely affect determination, that results in an informal consultation between the action agency and NOAA, and ultimately will result in a letter of concurrence from the services. If an activity, on the other hand, is deemed by NOAA to adversely affect a species, even if the action agency determines that it's not likely to adversely affect, then that activity results in a formal consultation with the services and ultimately results in biological opinions. And John, this is my second to last slide, just so we're all on the same page. And I should mention that the formal process can also lead to what's called a programmatic biological opinion. So if an action agency has activities that span a bit of time, they can forecast what those activities are, engage in willing monitoring of those activities, and we can have reasonable certainty of predictable outcomes to listed species as a result of those monitoring activities and those actions by the services. We can write what's called a programmatic biological opinion. And NIMS really prefers those, because if an action agency does what it says it does, or says it will do, it can result in a consultation that takes between 30 minutes and probably 12 days. The biggest factor of influencing how fast a programmatic biological opinion implementation takes is strictly workload. If you had nothing else to do, a programmatic consultation would take between 30 minutes and a day. By far and away, NIMS's activities result in formal consultation a minor proportion of the time. However, as you can see with the graph on the right, a formal consultation takes an inordinate amount of time. And we have a very large workload. This 176 days you see in time to complete a formal consultation on the right side of the graph is probably closer to 300 right now. So we've got a very big workload, a very big backlog. And if there's any opportunity to find a programmatic consultation that will work for an activity, we try and do that. Otherwise, we try and get the services to find activities to make their their activities less impactful for listed species, and potentially go to an informal consultation. The last thing that I want to talk about is briefly recovery plans. Section 4F provides for actions that lead to the recovery of listed species or a reclassification of listed species from endangered to threatened, or from threatened to delisted, or in some cases worse. You know, if a threatened species is imperiled a great deal more, and through a 5-year review we find that it's wandered into an endangered, we can go that way as well. Recovery plans are developed in cooperative agreements with federal, state, tribal governments especially, but also local government and non-governmental entities as well. And for that, Amber can talk a little bit more about that with respect to Puget Sound.
Okay, Amber, go ahead. Thanks.
Hey, great, thank you. That was a great overview, Dave. Let me share my screen. Thank you for having me today. My name is Amber Moore, and I am the Salmon Recovery Manager at the Puget Sound Partnership. And today I'm going to build off of what Dave just presented on and give an overview of our role in salmon recovery in Puget Sound, some background on the Puget Sound Salmon Recovery Plan, and how this aligns with local salmon recovery strategies such as Skagit. So just to orient you, there are 8 salmon recovery regions statewide, and Puget Sound is one of these. It's this kind of orangish area here. And our Puget Sound Leadership Council is designated in statute as the Salmon Recovery Regional Organization for Puget Sound salmon species, except for Hood Canal Summer Chum, which the Hood Canal region manages. You can see it's kind of embedded here within Puget Sound. And our Leadership Council has designated the partnership as the organization carrying out the work of a salmon recovery region on their behalf. Our Salmon Recovery Council, where the Skagit lead entity and the Swinomish tribe both have a seat, is the advisory body to both the Partnership and Leadership Council on salmon recovery policy issues. And in essence, the main responsibility of a salmon recovery regional organization is to coordinate implementation of their salmon recovery plans. So the partnership coordinates implementation and adaptive management of the Puget Sound Salmon Recovery Plan, which is mainly focused on Puget Sound Chinook salmon, given their listing designation as threatened. So the Puget Sound Salmon Recovery Plan for Chinook salmon was approved by NOAA in 2007. Chinook salmon, as I said, are listed as threatened under the Endangered Species Act. The recovery plan contains 16 local chapters, which are these blue circles here, a nearshore chapter, and a regional chapter, which is the orange circle at the end here. A group called the Shared Strategy Development Committee wrote the regional chapter, and this group became the Puget Sound Salmon Recovery Council in 2007. The plan is primarily focused on Chinook, but it also mentions bull trout, and many of the local chapters also have strategies for other locally and tribally important salmon species, such as coho. So the Skagit Salmon Recovery Local Chapter is one of these blue circles in the diagram. All of these pieces together make up the plan. And Washington is somewhat unique in that our salmon recovery plans were written by a coalition of groups coming together to write the plan, rather than NOAA leading the writing of the recovery plan. And this is part of what's known as the Washington Way, which I know all of you are familiar with. So you've probably seen this bold underlined piece here, but the overarching goal of the Puget Sound Salmon Recovery Plan is to recover self-sustaining harvestable salmon runs. This is what really guides us in our recovery efforts, in a manner that contributes to the overall health of Puget Sound and its watersheds, and allow us to enjoy and use this precious resource in concert with our region's economic vitality and prosperity. There are 4 parameters in the plan to describe viable salmon populations, or VSP, to help get us to recovery of Chinook salmon. That's abundance, which is the size of the population; productivity, which is the overall population growth rate; diversity, which is variation in genetic, physiological, morphological, and behavioral attributes; and spatial structure, which is geographic distribution of fish at all life stages. And then there are also specific measurable goals for specific Chinook salmon populations and their habitats in the local watershed chapters. So as I said earlier, our Puget Sound Leadership Council is the regional salmon recovery organization for Puget Sound salmon species, except for Hood Canal Summer Chum. and they designated the Puget Sound Partnership to execute the duties of a regional organization on their behalf. So the partnership works to coordinate implementation and adaptive management of the Puget Sound Salmon Recovery Plan. This includes updating the regional chapter of the plan, that orange circle in the diagram I showed you earlier, which is ongoing. We're doing that now, as well as working with the lead entities and partners to determine the highest priority salmon recovery actions to advocate for and undertake. We also support our local partners and co-managers and updates to the watershed chapters of the recovery plan. So this includes helping get funding for updates, hiring contractors to coach watersheds in making those updates, and ensuring that local priorities inform regional scale priorities and actions. We also help ensure that Salmon Recovery Funding Board and PSAR projects are linked to recovery chapter strategies, and we certify all of the lead entity project lists every year before submission to RCO and the SURF Board, which is one of our requirements as a regional organization. We also advocate for salmon recovery priorities at the regional scale. This includes elevating local issues with our state and federal partners and regional decision makers, working on policy improvements to aid salmon recovery, and advocating for more funding for salmon recovery at the state and federal levels. So as I mentioned, we're currently updating the regional chapter of the Puget Sound Salmon Recovery Plan, which should be complete by the end of this year. And the regional chapter of the plan is focused at the Puget Sound scale and is therefore broader in its focus. And the watershed chapters and strategies fit under the umbrella of the regional chapter and are more focused towards the need of the particular watershed and lead entity. We have been supporting our lead entity and co-manager partners to get funding for their local watershed chapter updates. 5 watershed chapter updates have been completed as of today, both by support we were able to provide and also funding that the lead entities were able to secure themselves. And 2 more are close to completion, hopefully this year. The partnership salmon recovery decision package was fully funded during the supplemental session, which includes funds to update the remaining watershed chapters over the next 3 fiscal years. And you can see how many we're hoping to support in each fiscal year coming up. So thank you again. That's pretty brief, but I'm happy to take any questions and look forward to the discussion. Thank you.
Thanks, Amber. Do we have any? Well, there's one, Jenna.
Yeah, I do have a quick question. Thanks for the presentation. Sorry, I was a little late. What's the public process for the update of the recovery plans? Do you guys spend time in the local communities when that chapter is being updated?
So this is the first time we're updating it. It has not, that's one reason why we're trying to do this full update of the plan, because it hasn't been updated and since it was written and adopted in 2007. So yeah, we haven't done this before, but I have been talking with the lead entity coordinators about the regional chapter update at our watershed leads meetings. And we've also been doing, bringing the different topics and strategies and actions to the Salmon Recovery Council for their review and input at their monthly meetings for the last couple of years. We also, once the update is, the final draft is completed, we will be circulating it for review to the Salmon Recovery Council and to the lead entities. So we're continuing to solicit review and input there. And then, of course, the lead entities, when they update their watershed chapters, they have their own kind of review and approval process locally.
So the public process is through the lead entity, and so that would be Skagit Watershed Council, since we don't have a lead entity, I'm guessing. Richard, I can see.
Well, I'll just note that our watershed chapter was developed a little differently. Of course, we have a set of co-managers that wrote the chapter and really have ownership for the Chinook recovery plan itself. And we support, facilitate, connect locally wherever we can. Our role at the Watershed Council has been the voluntary habitat project pieces, development and implementation of that. So we'd have a strong role in strategy development and local outreach, but it really is a co-manager driven process in the Skagit.
And so then is there a public process for the co-managers to update the recovery plan?
So these are good questions, Jenna. If possible, I'd like to just put them as very important for us to work out. But what we've heard from the co-managers so far is that we won't be updating the chapter for another year or two. So we're going to be later in that fiscal year process. But your points are very well taken, I think, by the team.
Just a quick
David, yeah.
Sorry, just a quick interjection. Ultimately, NOAA will approve the regional recovery plan. And as part of that process, we'll have a public outreach, and we'd be grateful to have the partnership and project partners involved in that process.
So let's go on to what's been completed, how's it working, and what might the future hold? And on my list, Eric, your name's first, so I'm going to turn to you and then see where we go from there.
So thanks for having Greg and I present. I'll start and Greg will finish, and they're listed on the agenda. Is also Mike Lemoyne and Corey Green, and they're not going to be presenting. In fact, Corey isn't available for the meeting, but Mike is here to answer questions on topics that he's working on, and both Mike and Corey have definitely contributed to content in these presentations and are PIs in some of the monitoring research work in the estuary. So we're going to flow through some things. I'm going to just, here's the outline. So I'm going to remind folks what our presentation was last time about the Chinook Recovery Plan chapter for the estuary. I'll blow through that really quickly, hopefully, but it is because hopefully you've seen those slides in the previous presentation or Science Summit series date. So briefly, I'll cover our monitoring approach. We look at project effectiveness and the whole system, the estuary system, either the population, if we're looking at fish, or the habitat, the whole estuary habitat system. Then gonna list what has been restored. So there's a series of projects that are built already and have been monitored, and I'll cover the results on the fish side of things. Greg will cover the results on the habitat side of things. And I think then we'll have questions, but Richard will spur from there about and have a conversation about the projects that are in the queue, as I like to say, are the ones that are likely to be built in the next few years. So that is all. Some of those are also on our list of when I show the projects that have been restored. I also list what we think are coming up, what's coming up, because we need to start monitoring those projects before they're built too. So, reminder of the recovery plan chapter for the estuary. So it's chapters 11 and 12. I'm lumping the nearshore in with this, at least conceptually, because a lot of the nearshore chapter, the Skagit Chinook recovery plan, is about pocket estuaries, and pocket estuaries are sort of a pseudo-natal estuary, an alternative rearing habitat because of the displacement that goes on in the natal estuary, the tidal delta. The biological processes are similar, so I just sort of lump these together, although this talk really won't cover the pocket estuaries. That would be a talk all in itself. Most of the science details about this part of the plan are found in Appendix D of the recovery plan. Reminder that we're thinking about Chinook salmon as a life cycle, life stage context. So we isolate the different parts of the life cycle and have recovery strategies for each life stage if merited. And in this case, we're focused on the estuary and the sub-yearlings that come to the estuary and take up rearing for a period of weeks to months. But I'm not going to show this part, or those fry migrants that rear in pocket estuaries or independent small streams also for weeks to months. But that's the part of the Chinook life cycle we're looking at. And so just some pictures of the habitat simplistically that we classify and sample fish in. So basically you have a series of vegetated wetlands, tidal wetlands that could be the classic salt marshes, emergent marsh, or scrub shrub habitat, or even tidal forests. We have all of that in the Skagit. And then there's fundamentally two kinds of channels There's the open-ended ones, the distributaries. So that's the river water getting out into the salt water. But it's also the plumbing for fish movement and other things like sediment and wood and those things. And then we have the tidal channels, and they're often blind-ended, and the fish utilize all these wet areas. So Greg will cover more of those, but you'll see some of the fish results may be related to the different channel types or vegetation zone. We also have the pocket estuaries, and they're something like Lone Tree Lagoon is a barrier estuary, and it has a puddle, I call it, the lagoon part where the fish live in, but also the creek. But I also like to show that there's a lot more going on to form and sustain a pocket estuary. You need to have healthy sediment sources and spits to build the berm so that you have the lagoon. So that's the whole thing with pocket estuaries. And I will have one last slide that includes some pocket estuary information, but that will be it for this presentation. So summary, why we stated in the recovery plan why we need estuary restoration. Quite simply, it was looking at the current habitat conditions compared to historic, some measurement of the biological mechanisms that occurring in those habitats by juvenile Chinook salmon, and then an observation that we had unbalanced migration pathways for fish to find habitat opportunities, and all that led to the identification that restoration in the estuary or the tidal delta and pocket estuaries is needed to support recovery of Skagit Chinook salmon. We used a stock recruit carrying capacity model to predict benefits of candidate projects, and then and I'll just show you some pictures basically from the recovery plan, just to remind folks what those data look like, because we'll pick up on some of these things later when we go through the monitoring results. So basically, both pocket estuaries and the delta are smaller in area, and they're fragmented, just the bookends of both habitats. So historically, the Skagit Delta was large and contiguous all the way from Stanwood to Padilla Bay, and now it's narrower and fragmented. Same thing with the pocket estuaries. The panel on the left is an estimate of historic pocket estuaries in the Whidbey Basin, and lots of dots. And then presently there's many fewer dots. And when you do the math of the wet areas that fish could directly live in, it's a huge loss, about over 80% loss for both habitat types. So for a life history types that depend on estuarine habitat, that can't be a good thing, to have much less habitat than historic to complete your life cycle. So fortunately, we've had a lot of monitoring that started a long time ago in the Skagit, and we were able to make use of that to measure fish response in the estuary and build that into the recovery plan. So one in these graphs, 1 dot equals 1 year's worth of effort sampling in the estuary or at the smolt trap. So these are the classic stock recruit curves that we had at the time of recovery plan, showing that more fish entering the estuary, the top panel from the freshwater outmigrants, doesn't beget always more fish or a linear relationship to more fish in the delta. So you see it start to level off. You have evidence of the habitats filling up or carrying capacity being achieved. And then the flip side, the bottom graph is basically a mirror image, only in reverse, where the size of fish declines dramatically and then begins to level out as continuing to be small fish in the estuary. So you see evidence of density dependence from 2 different measurements of the fish. And lastly, we see displacement as the estuary, or the number of fish that could go into the estuary, increases on the x-axis. You had more and more of those fish percentage-wise increasing in the bay as these really small fry migrant fish early in the year. So you had evidence of displacement. So all those things together was strong biological evidence that our Skagit fish under present conditions needed more estuary. And then we have this cartoon of the fish migration pathways, and the bigger the arrows, the more fish are using those pathways. And you can see not all the arrows are sort of equally branching throughout the delta. So this cartoon was beget from measurements of fish density across the delta, and also in the nearshore trajectory of where the currents go based on drift buoys. So this was plugged into the suite of projects that were assembled for the recovery plan, and the pink polygons, at least by my colorblind eyes, they look pink, are the candidate projects that were listed in the recovery plan, and they increase capacity because there's lots of new area that fish could get to. And then there were also 2 key connectivity projects to help replumb the delta to balance out those pathways and allow for fish to make better use available habitat or the potentially restored habitat. There were also a list of pocket estuary projects listed in the recovery plan, and some of those have been built and monitored, but that's a different, we don't have time to cover that story here. Okay, so that's the quick background on the recovery plan that was shown last time, but I think if you weren't at that presentation, at least it gives you some background, and those that were at the presentation, hopefully it reminds you of the context, because this is where now people went out and built projects, and folks like me and others are monitoring them and learning what's happened. So first of all, we monitor at a series of scales and because of their importance. So the first level is project level. So somebody builds a project and we'll measure fish and habitat within the project, and potentially if there's sort of infrastructure that's important, that may get monitored. A good example of that is the Fisher Slough floodgate, which was integrated into the monitoring design because it potentially had an effect on performance of the project as well, for biologically, but also for drainage and flooding. We also monitor at the whole system. So that would be for the fish, that would be the population within the estuary, or for habitat, it would be all the habitat, not just the restored habitat in the estuary. And answer questions about performance and pace and those sorts of things of restoration. And all this stuff can contribute to understanding at the region, and notwithstanding the ESA status review questions that NOAA might have, but also feeding into programs like ESRP, which one example is we co-authored a tide gauge study with NOAA, which looked at a series of projects, but it contributed to ESRP's plan for supporting different restoration strategies. So all these things are happening within the Skagit, and while we're starting local and kind of looking out to the region, we think our work is helpful to the whole region, and we do, as David mentioned, we do our ESA implementation within an ESU. So we're implicitly saying that our local populations, our local scales are contributing to a larger scale, the whole of Puget Sound. Okay, so next slide. And I'm sorry I'm hurrying, but I think we need to. What's been built? So there's been a series of projects built. So above the red line, those are all projects that have been built. And you may know the name of them on the far left, or you may know them by a slightly different name. This is a table out of our Skagit IMW annual report from last year. And it has a project name, the year completed, and then the type, fundamentally the type of project it is. It either improves connectivity or capacity or both those ideas. So when it's capacity, it's usually increasing the tidal footprint. So it's a new area or restored area to fish. When it's connectivity, it's restoring one of those distributary pathways or connectivity to existing channels within a footprint that's already tidally influenced or exposed to tide and river hydrology. Then on the far right, there's some data about how we monitor, and if we monitor, the years monitored. PT is post-treatment, BACI is before-after control impact. So that's your kind of our best type of design, where we monitor fish and habitat before and after the restoration, and we also compare it to reference sites. So in some cases, we were only able to do post-treatment design, where we went in after restoration and looked at what has happened, and but many of our projects are BACI. And then at the bottom of the red line, the blue, those are projects in the queue. And so you can see that we have plans to design many of those, and some of those are out of date where it says not designed or funded. Some of those have changed, like North Leckway is getting built this year, and it is funded and designed. In fact, our crew, Mike is out there monitoring this year for pre-restoration data set. So a lot of projects. Another thing to note is that for the recovery plan, Deepwater Slough got built, in year 2000, and it predates the recovery plan. So as far as contributing to the goals or objectives of the recovery plan, it predates it, but it's a super important project in the Skagit because we can learn a lot from it. And Greg will show some results about Deepwater Slough that's really important in thinking about what to do and how things are performing for the future. Okay, now I'll go to the Chinook salmon results. I'll cover project effectiveness and then some population response, and give some brief thoughts about what we're working on that's in the future, some of it in the very near future. Okay, so there is a theme, excuse me, for the local or restoration project fish response. And that is, if you build it, they will come. And that's, everyone's heard that. It's that term, it's simplistic, it's fun to say, but it's really true in the Skagit. Every single project that's been built in the estuary does get used by juvenile Chinook salmon. And in most cases, the juvenile Chinook salmon densities are consistent with reference sites. So that's overall a really good thing. There is a little bit of a caveat, and that is that some designs work better than others. And that's what I'll mostly focus on. But sort of the punchline is, if you restore the hydrologic processes well, that like gets done with dike setback, dike breach, or fill removal, those are the projects that work the best. If you're muting the hydrologic processes, those projects tend to not work as well. The first example of that is a tide gate replacement project. This project occurred on Swinomish Reservation as phase 1 of Smokehouse, and it's the South Hornsby tide gate. And the tide gate's pictured there, and the blue dots on the outside in Swinomish Channel were fish sampled and compared with the fish samples collected at approximately the red dots within upstream of the tide gate. So to keep the presentation short, I'm not actually going to show the fish data. The fish data I often do, but I'm going to show you the punchline. So what we're doing is we sample by beach seine every 2 weeks from February through mid-August. So a lot of sampling, a lot of potential catch, and we compare that as a curve on the seasonal curve. And so I'm taking the ratio of cumulative or seasonal fish density from the inside upstream of the floodgate compared to the outside. So you have a ratio. If you have more fish on the inside, the ratio is bigger than 1. If you have more fish on the outside, the ratio is less than 1. And so here's the results for a series of tide gates, but this is reflective of South Hornsby. So it was a traditional gravity-fed flat gate. It's meant to keep water, tidal water out of the system upstream of it, and it generally does a pretty good job of that. Although sometimes they leak, and when they leak, they sometimes have fish, and this one leaked a little bit, and so there were some fish in there, but way less, many less upstream of the traditional flap gate than on the outside. After a self-regulating tide gate was installed, you saw a bump. So there was an effect on fish, juvenile Chinook salmon densities upstream. It's actually a little bit more than double what the traditional tide gate was, but it pales in comparison to reference sites. So we would want, in a good restoration technique, we would want to have the treatment effect to be similar to the reference sites. So so the self-regulating tide gate did improve fish Chinook salmon use upstream, but it's about an order of magnitude less than what you would expect with a paired reference site. So there's actually I think 4 different kinds of designs, but I'm going to go to just the dike setback and dike breach ones and forego showing you the fill removal, because the dike setback and breach ones are often the very largest projects, and then these are projects that will also link to what Greg is talking about later on. So Wiley Slough has a dike setback project. So I don't have a great map here, but the dike prior to restoration went around on the outside perimeter and out of view here, and excluded fish use to historical channels here that were mostly drained, and at least the wetlands were, and then restoration allowed the Wiley side of the project to be tidally inundated. This is on the bay side of the spur dike that probably most of you guys know about. And then the Teal Slough side, which we divided into 2 lobes, the southern lobe and the northern lobe, from monitoring standpoint. And this is the boat ramp at Wiley at the island unit area. So just show you some plots of the years one of the years that we sampled. So you see a really nice curve in the Wiley lobe for 2013. And it would note that there's, in April, there's upwards of 5,000 fish per hectare of either blind channel or impoundment on these ponded areas. So a lot of fish in that area. And then same thing in the south end of Teal lobe and the north end of Teal lobe. So lots of fish, a seasonal curve. And we have a report about that, all that. And this is just one of the years. We had 2 years that were monitored, but basically before restoration, we didn't monitor because the site was blocked off. And the assumption is there was either no fish or very few fish there. The side note is subsequent to what we've done at Wiley, or monitoring at Wiley, we always try to sample, if there's water, we always try to sample inside the restored area, even if we think it's blocked off, because the lessons learned that sometimes these tide gates leak, and there's at least a few fish already living in there. So it'd be good to know about that. But anyway, the 2 years after restoration that we monitored, I believe it was 2012 and 2013. 1 year we estimated 88,000 fish lived in the collective system, and the other year almost 250,000 fish lived in the system. There are 2 different outmigration size years. This 250,000 year was one of the larger outmigrations. And then when we compare on record in the Skagit, it was upwards of 5 million, if I remember. And then when we did the math on the amount of habitat using our carrying capacity model, if you count only the tidal channels, then you get a carrying capacity of 75,000 fish. If you count the tidal channels plus the impoundments that were present when we monitored, and you get a carrying capacity of 370,000. Really, really different numbers, and that matters a lot probably for achieving goals of the recovery plan, because the recovery plan is for the estuary, the strategy is to increase carrying capacity by 1.35 million. So it would matter if it's 75 or 370,000 fish. But this is where Greg's story comes in. We're learning about what the trajectory of restored habitat is. And not to rob his story, but that we're seeing this area revert towards less impoundments and more tidal channels. So the reality is we'll get what we get from whatever is sustainable habitat, and it's on some kind of trajectory to a norm, which these are the models that Greg works on. Another project for Island Farms. This is a dike setback and breach design, and this is this is on the bayfront. It was monitored as a backy, really well supported in monitoring, and I would want to note this is a large site. I think I should remember off the top of my head. Sorry, Jenny and Jenna, if I get it. I think it's 130 acres. But it has one breach, which Greg will, more from Greg on that. When we look at a project of this size, we generally see more than one breach, but it doesn't mute the hydrology, like you get full filling of the area with the tide, but it may change some things that we didn't know about when we went into designing projects like this, and that now we can feed back into the project or into project design. So in the case of fish monitoring, we monitored it well 2 years before and 2 years after. And you saw that tide gate at that site did leak. So we did have a few fish in the little bit of habitat that was there. And then after restoration, we see a mirror or an exceedance where there's more fish inside the project area than adjacent or those reference sites. When you do the math of this site, we observed 1 year, this small year, about 8,000 fish inside the restoration project, and the larger year, again, this was 2 different outmigration year sizes. The larger year was 50,000 fish was the estimate that used the project. And the carrying capacity estimate for this site is consistent with the 50,000 fish carrying capacity lift. So in summary, kind of going back to, I already showed you this comparison for tide gate restoration, which I would advocate is not a very good way to achieve salmon recovery because there just physically isn't enough sites and area to achieve the goals of recovery plan, just getting a bump of a little bit. But fortunately, dike setback and dike breaching does give you a big lift. So all the sites that we've monitored are consistently higher or equal to or higher than reference sites in the Skagit. Fill removal also works really well, but fill removal is really expensive. So it's only really been done in the Long Swinomish Channel, and it works really well. It can do 1 to 3 acre sites pretty cost effectively, and it's probably, we're advocating that that's a reasonable strategy along Swin Channel, because Swin Channel is just vacant, essentially vacant of habitat opportunities along it. It's a dredged navigation channel instead of a historical meandering distributary. But nevertheless, there's some large restoration areas at the north end that smokehouse tide gate that I showed you is going to become a dike setback area. That's towards the north end. So having a safe corridor for fish to get to those larger restoration opportunities is a good idea. But so fill removal completely, it is a full process restoration. You're just basically excavating down to the historical marsh elevation and getting the tide to work the system. Last project type, and then a couple more slides, further thoughts. So there's complex projects too, like Fisher Slough. So you had floodgate operation with dike setback. So you have Fisher Slough, you have a floodgate or a tide gate at the road crossing, railroad crossing, and then you have a dike setback area in addition to the approximately 12 acres that was there historically. So floodgate, we had a conceptual model when we monitored Fisher Slough to try to tease out the restoration effects. So basically we had this diagram that you would have fish passage if the doors are open. Obviously a fish couldn't get through a closed door system and access habitat. So if you had doors closed, then you didn't have fish passage. If you have them open, you might have fish passage. Has to be deep enough water. In the case of Fisher Slough, it was pretty much always deep enough, so we could continue to have fish, possibly have fish passage, depend on the tidal stage. So if it was ebbing tide, so flowing downstream, these small fish may not be able to swim upstream against that, so you wouldn't have fish passage if that was the case. Or if you had a no current or flooding upstream, so we called that non-ebb tide stage, then you would have fish passage. So what we found in our monitoring that in fact, this non-ebb tide stage, the amount of time that you had non-ebb tide stage at the site really predicted how many fish you got into the site. And so we monitored 3 years, 3 years prior to dike setback, 2009, 10, and 11, and then 3 years after dike setback, 2012, 13, and 15. We didn't monitor in 14 fish. So these are the percentage of hours in a day that for the time of year that Chinook salmon could utilize that site. So that February through August time period, that hours in the day that the tide gate was open and at non-ebb tide stage. So you can see some days, very few, it was open all the time. So for whatever reason, it's not flooding. It's not flood tide that whole time period, but you have some days where the river's rising and the gates are open, and you have non-ebb tide conditions. But on average, these median lines, you can see that it's more hovering around 10 or 8 or so. There was a floodgate replacement. The old floodgate was in existence through 2009 and then replaced, and then we had a new floodgate, which had a various operation levels that were unique to humans operating the tide gates, but also very unique to the flow years of the year. So in the case of 2015, which is really interesting, the gates were held open 100% of the time when the fish rearing period, but it was a really low Skagit River flow year. And so in effect, the site performed for fish access among the poorest of any of the years, with the median distribution being right around that 7 or 8 hours a day. So that is background on how the tide gate worked. But when you added on, so here's the plots of fish abundance for all 6 years. So the first 3 years are no dike setback, and then the second set of 3 years is with dike setback. You can see that there's many more fish at the site after dike setback. And so there's a strong treatment effect of having dike setback. It's a really good idea, even with the floodgate, to have that dike setback. That's how you get the biggest bang for the site, is having the dike setback. But you could still see there was an operational effect on fish abundance too. So we took sort of the upper and lower quartiles and showed the model predictions for abundance with low fish passage potential. So that was 115 hours in a 2-week period versus 170 hours over a same 2-week period. And you see that there's a pretty big difference between low and high fish passage. So you can here's this prediction for peak time. And that was about 30,000 fish using the site with the dike setback condition at high floodgate operational procedures. So this is really good information to help understand the fish use and benefits from complex projects. With more and more, we're going to have those kinds of projects because there's a lot of infrastructure across Puget Sound. And I'm really happy that we're able to tease out the effects, the 2 different types of effects, and be able to tell the story at the site. Okay, pretty simple system population response. Going back to the simple bullets are juvenile Chinook are less crowded with the restoration because it's increasing area. The length of residence in the estuary is increasing, and that's a good thing because then the fish can set up for residents in the marine waters better by growing more. And then we are seeing a small signal, but it's too early to say conclusively, but we're seeing as the right direction, that we're reducing the number of fry migrants, and we're getting a higher higher small to adult return rates as a function of restoration. But the latter one is the hardest one to tease out statistically, because there's a lot of other variation that occurs after the fish leave the estuary that we have to account for. And it takes a long time to wait for the fish to go out to the ocean, live a couple years, and return and account for them. So the process is much slower in getting that data. But going back to the very first Chinook recovery plan slides I showed you, where there was only about 11 dots or 11 years, now we have about nearly 30, and we're still seeing the same theme. So this is that stock production curve. So the number of fish that could go into the estuary coming out of the river, and a function of their density. So we're still seeing the same curving relationship. We're still seeing the reduction in size. We're still seeing that fry migrant response, but we're learning some things. So we can see that temperature has a negative effect on growth, and or an offsetting function on growth. It primarily is removing the time that the fish can live in the estuary. So there's a shorter rearing period. But when you add on wetland area, so restoration, we're seeing improvement in growth. We're also seeing a new thing. So we're seeing an increase in residence time. This is a plot of a surrogate for residence time. So the 50% time fish are the date that they're in the estuary. And we're also seeing a bump or an improvement in residence time with wetland area or restoration. And then we've also shown this a little bit simpler graph where cumulative restoration as a function of residence time. That was in one of our earlier reports, the 2015 report. So we're seeing really good information at the juvenile population stage. So, and in response to restoration, we're seeing a hint in the adult to recruitment, but again, that takes a long time to get those data. So we're encouraged that if you do the restoration right, not mute processes, you're going to get a bump. So it begs the question if current restoration projects are enough. And I just want to go back to our slide from the Chinook recovery plan, that while we've done a lot of restoration, we still have more to go, but it also really hinges on protecting the existing habitat, including the existing estuary habitat. And there'll be, Greg will touch on that, and Richard's going to touch on the projects in the process in the queue. So currently the number of projects built, of course, doesn't achieve the recovery goals for the estuary strategy, but there's more to the story there. And there's optimism, I would say, that we could get there if we built the projects and we build them well, because we know they work. Again, reminder that the recovery plan has a goal of a bump of 1.35 million capacity. Also a reminder, there's some projects that optimize or improve existing habitats. So something like McGlen Island, if you restore connectivity, you get a bump in the existing habitat just by having it better connected. Plus, there's a lot of restoration opportunity. This is just a figure out of the recovery plan that would have to be redone if McGlen were to go to a specific design. So new predictions could be made. We need to continue our monitoring, and I guess I would want to highlight that we need to continue collaborating. We collaborate with NOAA and WDF&W, but we also collaborate with local partners like the Enhancement Group and TNC down in the Stille tribe. So all that is super important in our learning. And there's a couple of themes that I want to highlight that we need to learn more about. And that is, I think we went into the recovery plan thinking that density dependence and carrying capacity was really simplistic, and it's not. So we have that evidence of density dependence, but it's not just purely the stock recruit curve that the estuary fills up, and it fills up magically and evenly, and then excess dies or goes downstream. It's actually, you see other responses. So you see response in growth, you see response in prey selectivity. So it's more complicated than just filling up. We learned that from Four Systems study, which I have referenced here. But one of the big things that came out of that study is that there's, even when you have a stock recruit densities across the estuary, there's lots of times and places throughout the season where you don't have fish observed. Now the Skagit, these are plots of percent where sites that are present by month, fish are present or Chinook are present, but that's not 100% in any case. Skagit is the highest, but all these systems had plenty of times where you have density dependent densities, overall densities, but there's sites that don't even have fish. So we're saying our human view of capacity probably shouldn't be so simplistic, and maybe a better model is something like the freeways and gridlock, and it messes up the system like Seattle, our estuary. But when you get onto the side roads, you still find roads that aren't in gridlock. So maybe ecologically, Chinook and estuaries works more like the traffic model than a parking lot or hotel rooms that are filled up completely. There's no vacancy. So we need to learn more about that. We also need to learn more about location. I won't explain this so much, but where habitats are really matters, and it always matters. It always predicts densities. So closer to the source of fish always have higher densities. Other like habitat quality being equal, and places distant have less density. That's why that connectivity is so important in Swin Channel. But it's even, and we found that true in all four systems that we studied, but it's even true system to system. And so Mike recently completed a report that was for the Stilly Estuary, and we found more than 50% of the fish in that northern part of the Stilly Estuary were Skagit origin fish. So things are connected. We need to learn more about that. Thank you, Stilly, for restoring habitat for the benefit of Skagit fish too. The presentation has a list of the references. You won't read them, but the archive, you can access the reports. And that's all I got.
All right, so I'm going to take up where our Eric left off and talk about habitat. So the question we're left with, is there more estuary habitat for fish? And to answer that, we need a large scale perspective, and that's where the status and trends monitoring comes in. And Eric's been talking a lot about this large scale perspective already. So the Skagit Estuary is gaining more habitat than it's losing. That's good news, but we have to keep in mind that there is loss occurring. There's gain occurring, and primarily because of habitat restoration. But there are also natural gains and losses that we have to keep count on to basically have a net, calculation of net habitat gains. And so that's what the habitat status and trends monitoring is about, is accounting not only for anthropogenic habitat gains and losses, but also for natural gains and losses. And so most of the losses that are here in red are occurring along the bayfront of Fur Island, which is sediment starved because the cross island distributaries, historical cross island distributaries like Dry Slough and other sloughs have been diked off, and therefore there's no longer sediment being delivered to the bayfront areas. And so those marshes have been eroding away, and we can see that going back as far as 1970. 1970 was kind of like the peak of the bayfront marsh extent, and it's been eroding ever since. So, and we're losing, of course, marshes. Can you see my pointer? Okay, good. So we're losing marshes down here in the South Fork as well, and so that's a bit of a concern. And a lot of this seems to be due to wave attack. So areas that are sheltered from waves, like we have a few outcropping rocky areas in the bayfront area, especially the north end. Those rocky outcrops protect marsh in their lee, but areas that don't have that kind of protection are getting eroded away by waves. So what we see here is habitat trends over time here. So I'll focus on the bayfront. We've got vegetated tidal wetlands that are the blue bars, and the yellow bar here is blind tidal channel habitat. And in the bayfront, we're having a slow erosion of that habitat, and then we get a bump in it when we do some restoration. So the Wiley Slough restoration, you know, that's northward of the spur dike, that had a bump of habitat, but then we still had continuing natural losses, erosion of bayfront marshes, and we get another bump with Fair Island Farms. So we're kind of playing catch up here with natural losses, at least when it comes to just these bayfront restoration sites. Unless, of course, at some point we restore sediment supply, sediment delivery through restoration of cross island, some kind of cross island distributary. Now in the North Fork, it's an interesting story because we've had an avulsion in the North Fork. So we've had kind of steady habitat, at least within recent decades. And then we got an avulsion that began in 2004, but was still a very small channel. Then it picked up steam probably around the mid-teens and became a steadily larger channel. And you can see that we're getting more and more, it's kind of hard to see at the scale here on this graph, but we're getting more and more blind tidal channels. And that's because the downstream part from the avulsion is filling in with sediment, because the flow is now directed through this blue area where the new avulsion is. That's gotten quite large. It's become the main stem essentially of the North Fork. And so this downstream area that's filling in is being, and some of these old distributaries are being converted into blind tidal channels. So we're getting more blind tidal channels as a result of that. And we're losing, of course, some distributary channel habitat, which you see down here in these orange bars. And we're getting some marsh habitat also because we've gotten some progradation right here at the mouth where my arrow is pointed. We've also getting some marsh development here in this part of what used to be the mouth of the old North Fork, and of course we have marsh development here on what used to be a branch of the North Fork, but that's filling in dramatically. So we have to keep track of these natural habitat processes as well, as I said, as the restoration that we're doing intentionally. And so here's a kind of an accounting of restoration by habitat areas. And you can see kind of a restoration over time. This yellow area is Fair Island Farms. And you can see there's kind of a cumulative rate of restoration that we can graph from this accounting. And so the question we can take from this now is, well, at this rate, how long will it take to get a desired future condition as to restore enough habitat to recover juvenile or to recover Chinook salmon, So we can look at this graph in two different ways. One, we can take a really optimistic view and look at the most rapid rate at which we've observed restoration occurring, or we can take a more pessimistic view and look at kind of the more the slowest rate at which we've observed restoration occurring. And if you do that, we can reach desired future conditions at a very fast pace. We can reach it by 2045, but at the slower rate, it's going to take till after 2100. And because we have natural losses occurring, we need more habitat restoration if we're taking a long time to restore it than if we do it more quickly. And so that's kind of that in the nutshell. So we really need to be moving a lot faster than we're currently doing at kind of the more recent slower kind of rate of habitat restoration. So there's a little bit of uncertainty in these estimates. And the reason for that is that there's some statistical uncertainty in the models that we're using, of course, that's just natural. And then habitat is not static. I'm going to go into that in a little more detail in some of my future slides. So one of the things that happens when we do restoration is that sometimes you don't restore precisely to the natural template, and sometimes we over excavate some areas, and that's exhibited here by this diamond. And sometimes we under excavate tidal channels, we underbuild the restoration site, and it takes a long time for these systems to move towards kind of a natural template, natural expectation. And so that's going to affect the rate at which we recover habitat and recover fish. So yeah, impoundments and development of channels, and I'll go into that into more detail in some of our future slides. And then vegetation colonization is another consideration that changes over time. And one concern is non-native species invasions, and that's something we are also monitoring. We have an intensely monitored watershed monitoring project involving non-native cattails, potentially displacing sedges, which are waterfowl food plants, for example. And so this is kind of a repeat of that previous slide, so I'm going to skip through it. But we have a lot of projects that are, in one sense, overbuilt because they have large impoundments, as Eric was mentioning earlier. That's what we see here in the top graph. And we have a lot of other projects that are underbuilt, and mostly it's because they have too few dike breaches and tidal inlets. And so I'll show you a few examples in some of our next slides. The stuff I've been talking about, and actually that Eric and I have both been talking about, we've been talking to some degree about models and using those as kind of like expectations. So I'm going to talk a little bit about predictive models first before I go on, because predictive models are really critical for habitat restoration. And we, I think in general, in the Pacific Northwest and in Puget Sound more specifically, and we haven't been using them as much as we should be. They're relatively new, I suspect. 30 years ago, restoration predictions were conceptual and qualitative. We didn't really have any predictive models. And so the idea was basically that, restoration sites should look and act something like a reference site. And over here on the right, this is when I was in graduate school, my RA was to compare this excavated channel here on the left that the Corps of Engineers excavated as mitigation for some dredging impacts, and it was compare it to this natural channel, and you can see just eyeballing it, they don't look the same. And it turns out that functionally they aren't the same either. I won't go into details, but my dissertation work was involved and was part of that. This channel used to have, the mitigation channel used to have a large subtidal component because it was mandated to have a big subtidal habitat component because that was what was impacted by the dredging. And as you can see, it's filled in with sediment. This is low tide, and you can see a bunch of mud. So clearly wasn't a sustainable design. And that's one of the things we're now starting to understand better with some of our predictive models. And basically, just winging it for restoration design is not good enough. And that's basically what was done here back in the late 1990s. Because we didn't have as good an understanding of systems as we do today. So we were winging it, and there's still some winging it that occurs to this day, and that's not good enough. We need to use predictive models more. So I'm really advocating for prediction, for planning and design, to evaluate and monitoring, and I'll give you some examples of that. And in general, to better understand our system, and then to advance restoration science and practice, because if you're not making predictions, you're not doing science. So I'm gonna to take a little step back and just talk about the model that's probably most commonly used right now in the Skagit and starting to be used in other areas as well. And that's the idea of channel allometry, which derives from the fact that landscapes are fractal. There are scaling relationships between different parts of the landscape and space between marsh islands and tidal channels, and power functions that describe fractals or allometry can be linearized by transformation, by logarithmic transformation. You get a straight line. Or you can just transform the axes, which is what I've done here in these graphs. And we see we have axes on a logarithmic scale, and the untransformed data graphs as a straight line when you do that. And so you have these nice relationships that are basically can be used to set expectations. This is what the natural world looks like when you observe it. It's actually fairly regular, and it's not random. And so we can then use that as a target for our restoration designs. I've also been developing some predictive vegetation models, and basically what you do is you go out in a wetland, and with an RTK GPS, you take a bunch of point samples of elevation and vegetation simultaneously, and you can get a frequency distribution curve for the occurrence of elevation at different elevation, the occurrence of vegetation at different elevation bins. So here I have Carex lingbii in the dark here, these dark bars. You can see that it kind of peaks at this particular elevation in the marshes, and then cattail, the non-native cattails at higher elevations. And at lower elevations, you have spike rush, Elaeacris palustris. And reed canary grass also tends to peak at higher elevations, but it's not very abundant in our tidal marshes. And this was put to the test in a paper that I published in 2013 with a manipulative experiment where I mowed cattail in part of the Deepwater Slough restoration site, a 3-acre area, and I modeled what the vegetation expectation would be. And what you see here is these yellow areas over here in this left figure are where cattail has a high probability of persisting. This area was originally all cattail. And then over here in the middle figure is where you predict where Carex lingbii would be dominant, the sedge, the native sedge. That's an important waterfowl food plant. And so after I did the mowing for several years, in fact, we had persistence of Carex lingbii. And you go out there to this day, I think this figure is from like 2019 or 2017 on the right, this aerial image. It's the green are the sedges, which are primarily Carex lingbii, also some spike rush, which is another type of sedge. And then the tan areas are the cattail that are persisting at higher elevations. So you can see that we can do a pretty decent job of making some vegetation predictions. We're still working on improving this model, but it has a lot of potential. And I'll show you some more examples of how we put this to use for restoration. Here's an example. This is one of the restoration sites in the north end of the Scilly Delta that is benefiting Skagit fish as well as stilly fish. This is the Zisaba site. And in the upper left figure, you see the vegetation prediction for what happens, what we should get after we restore the site. And it's predicted we'd have a dominance of Bulbochinus maritimus, which is a maritime bulrush. And you look at this figure down below, and that's exactly what we got. It's just a vast meadow of maritime bulrush. And we got that extraordinarily quickly. By the second summer after restoration, the site looked like a natural marsh. It looked like it had always been a marsh. And it was just stunning. In my 30 years of doing this kind of work, I've never seen a restoration site recover so quickly. Now, in comparison, Fair Island Farms is not quite so successful. Here's the predictive model for vegetation for Fair Island Farms. And this was developed on vegetation that was to the seaward of Fair Island Farms project itself. So went out there in those marshes, did RTK GPS, created these vegetation frequency of occurrence plots, and then translated that into my LiDAR data for elevations that I had. And then you can plot that, the lowest parts of the elevation of Fair Island Farms should be extensively populated by Chenoplectus pungens, American 3-square. And then the rest of the elevation of the site should mostly be soft stem bulrush, Chenoplectus tabernamentani. And then, to some degree, some Carex lingbii, and cattail should not be a problem at all for that site. And what we got instead was this. We got a lot of bare mud out on the site, this low growing green stuff that you see kind of, in a large part of this photo. That's a non-native plant, brass buttons, which is from South Africa. And then right along the dike fronts, the setback dikes, that's where we have some of our desired species that we were expecting, some of the maritime bulrush and Chenoplectus pungens and things like that. Now, why does this happen here at Fair Island Farms? Why is Fair Island Farms so far so unsuccessful? It's been 5 years now, and it looks pretty much like this. Whereas Zisaba was an instant success. It was like incredible. Well, I think the reasons for that is the tidal channel networks were vastly different between the two systems. So at Zisaba, we used the allometric model to make predictions for the site, and we excavated tidal channels in that system to match those predictions. And so we have an extensive tidal channel network in that site, whereas at Fur Island Farms, we have way too few channels compared to what we should have. So for example, predicted channel length is 11,000, almost 11,000 meters of channel, 11 kilometers of channel. What you actually observe on this site is a little over 2 kilometers, 2,200 meters of channel. And this is the 80% confidence limit of the prediction here in parentheses. We're not even meeting the lower confidence limit of the prediction here with Fur Island Farms. We have only one channel outlet at Fur Island Farms, and we should have 22, and at least 11 at the lower 80% confidence limit of the prediction. So what I think is going on is that when the tidal exchange occurs at Zisaba, a lot of that tidal energy is confined to the blind tidal channels, and relatively little of it is over on the marsh surface. Whereas the reverse is true at Fur Island Farms. There's relatively few tidal channels, so a lot of the energy of that tidal exchange is on the marsh surface. So we have high shear stresses, this is the hypothesis anyway, that are washing away seeds. And the reason we see a lot of brass buttons is because it has an unusual seed. It has a seed that has a mucosal coating on the seed that allows it to stick to the sediments. And it's probably, I'm guessing, an adaptation to its native environment where there was a high wave energy. And so that allowed it to colonize high energy environments. And that's what it's doing at Fur Island Farms. So that's a hypothesis that we're testing currently with additional follow-up monitoring. Basically, I'm going out there and doing some experiments, putting out seeds and some test plots in areas of high and low shear stress and at both Zisaba and at Fur Island Farms, as well as a couple of other sites. And I've also got a graduate student who is going to be doing some three-dimensional numerical modeling, and she's going to model the shear stresses numerically. And so we're going to have both a theoretical numerical approach as well as a observational empirical approach that hopefully will tell a consistent story. And if we do have convincing evidence, then we may argue for going back for some adaptive management and excavating some channels. The other issue for Fur Island Farms and for Zisaba, both actually, and for some other sites, is that a lot of these sites have a hard pan underlying them that might be formed as a process of agricultural activity itself, because agricultural activity can cause plow pans underneath their soils that limit hydrology. And so in this case, these clay hard pans underneath these restoration sites are limiting channel erosion. So if we don't excavate the channels, it's going to take a very, very long time for them to excavate themselves through that clay layer. And the clay layer is pretty deep. It's shockingly deep in some of these sites. Now I want to move on to some other sites. And so I'm going to go back to one of our first restoration sites here at Deepwater Slough Phase 1. And what you can see here on the left photo is the site as it's being restored. So you can see the dike over here on the left is being pulled back. Here you can see the dike is gone, and here you can see the dike is still present. And to orient yourself in this photo, this red material, this red part of the image is cattail, and this pinkish, whitish area is reed canary grass. In 2002, shortly after restoration, we had a kind of modest flood event, not a particularly big one, but it dropped a bunch of sediment. We had what's called a crevasse splay event here, where through this tidal channel that was originally present outside the dike. You can see up here, you can barely make it out through some of the shrubs. The river spilled a bunch of sediment onto the site, and we had this kind of fan of sediment and a channel cutting across as a result of that flood action into the site. And in the 2012 LIDAR, you can see this is before. Well, you can see that the kind of the elevation gain that has occurred as a result of that splay of sediment. And on that, now we currently have tidal shrub vegetation growing, which is pretty exciting to me as an ecologist, maybe not to a lot of people. But it's really interesting to see that that we're basically getting some habitat diversity as a result of this event occurring. And by the way, the 2012 LIDAR was taken before there was a significant amount of shrub. There were like maybe one or two small patches of shrubs here. So this is an issue. This is really truly bare earth here that we're seeing.
Hey, Greg.
Yeah.
How are we doing slide wise? We're almost 10 minutes to 12 here.
I'm going to finish up as quickly as I can here.
Okay, thank you.
So the other thing I want to point out is that the display is here in this lower left or this kind of middle left area of the site. But we have some other pre-existing tidal channels that were outside the dike. And you can see that this is the 2003 LIDAR, that high elevation was basically lined up with the edge of the original dike. But by 2012, we have sediment spilling across where all these channels are. So these channels are basically routes, pathways for delivery of sediment, and they're increasing the elevation, locally. And if we look at the northernmost area, we can see that here we also have shrubs developing in that new high elevation areas. So these small channels are really important for bringing sediments in and changing the vegetation. Oh, one more thing I wanted to point out here. The 2012 and 2019 LIDARs are similar in scale. The 2003 was a very coarse LIDAR, but the 2012 and 2019 are pretty good LIDAR. And I've coded them similarly. So they're identical color codes for the elevations. And what you see if you compare 2012 to 2019 is 2019, the site's starting to fill up with some sediment, especially in this area down here in the lower left. And also over here at the lower right, we have sediments that are kind of filling in the site and changing the elevation. And this is going to be a bit of a theme. So here we can see 2004, 2013, 2019, so forth for both Deepwater West and Deepwater East. And we have, in general, there's shrinkage of some of these ponds. These ponds were excavated historically and were pre-existing on the site, and they're shrinking to some degree. And we're getting tidal channels developing as a result of those ponds shrinking and becoming tidal channels, essentially. It's very dramatic here with Wiley Slough. Wiley Slough, after the site was restored to tidal exchange, had these massive ponds, and it wasn't really clear why they had them. If there was some problem with drainage or what was going on. I think to some degree, some of these channels had some, like for example, up here at the north end, this channel, as I recall, going out there had like a little natural levee that tended to keep water from going into this what it was, I guess, originally a drainage ditch. And so that kept things ponded. I suspect there was a lot of that because as they were cleaning these drainage ditches over time, they would just kind of sidecast the sediment that they would drain out. So you have these kind of little anthropogenic levees along the ditches. But for whatever reason, those levees have been breached now with new channels eroding through there, and those ponds have been shrinking. Also, I think there's been sediment has also probably been accumulating, settling out as the tides come in and go. And so for that reason, ponds are probably getting shallower as well. And so, as Eric was mentioning, these ponds support a lot of fish, but they're not sustainable. Over time, they're going to shoal up and disappear. And that's what we're seeing on a variety of these sites, including the very deep ponds at Deepwater East, the ones that were excavated. So, getting back to things moving from one condition to like the natural template, their adjustment over time. This is what we see here for channel outlet count. The Deepwater East and West are right here, and this is Wiley in green. And you can see that over time, we're getting more channels eroding across the former dike footprint. All these sites had a lot of tidal channel network already present because especially Deepwater East and West were never well drained. They were never well converted to agriculture. And that's one of the reasons why they were restored is because WDFW really didn't have much use for them from the point of view of having basically creating farmland for waterfowl food. Anyway, so these X's here mark the area channel surface area and channel length if you include the ponds, and the circles are if you don't include the ponds. So you can see with the ponds, they're really hugely out of line compared to the reference, but they're moving towards the reference as they fill in. And another point I want to make here is that when Deepwater Slough was first restored, we didn't have the allometric model at that point, and we had no idea how many dike breaches or channel breaches, because there should be. The dikes were removed entirely, but the main channels, the remnant channels that were on the site, only 3 of them at each lobe, Deepwater West, Deepwater East, only 3 of them were reconnected to tidal channels outside the footprint of the restoration site. So, and we actually wanted to have more of those connected, but the Corps of Engineers project manager at the time just made an arbitrary decision, said, no, we're just going to restore 3 on each lobe. And I don't really know what his reasoning was. But nowadays we know that that's far too insufficient. And as we saw from my graphs showing, or my figures showing you the vegetation change and the sediment delivery from just those channels that were outside the site, that weren't even on the site, they didn't even cross over the site, but they were just near the site. Those breaches are important, not just for fish delivery, but also for sediment delivery and for vegetation change over time. Okay, some lessons learned from Milltown Island. One of the things I think is really exciting about Milltown Island, this is a former farm site that was basically breached by floods and abandoned, sold to DFW, and then some occasional kind of ad hoc restoration efforts were made since that time. What we see on the site, these red dots are beaver dams. So we really have not been doing much with beaver. We haven't really given much thought to beaver, but there's beaver and tidal systems. I wrote a paper about that. They do a lot to increase the amount of low tide habitat for juvenile salmon. They triple the amount of low tide habitat, and they triple the density of fish within those ponds. So they're likely very important. And what we can see here is that they can reoccupy these former agricultural sites, and pretty extensively. The triangles show beaver lodges, and the red circles show their dots, show their dams, low tide dams. The other interesting thing that's happened here on Milltown Island is that we had this ad hoc restoration. We did some experimental excavation of channels through explosives, and in some cases it was successful, and in some cases there was failure. So this is an example of some successful explosions, these blue channels where things were exploded, and those channels have persisted to this day. And we even have beaver dams being located on some of these exploded channels, which is kind of amazing. Here's some more examples of exploded channels, but in some cases they weren't successful. So you can see these red channels, again, beaver dams on the exploded channels, but these red channels failed. And it's unclear. It's probably because we didn't, again, it was kind of ad hoc. There wasn't really good planning or design, and we need to think more about spacing of tidal channels in these systems to make them persistent. So just some summary thoughts about what we've learned. Deepwater Slough, there are too few channel outlets initially, but they are developing over time. Channel outlets are routes for sediment delivery, topographic change, and vegetation diversity, as well as fish delivery and fish access to the site. There was a large remnant channel network. It was never well drained or farmed. So channels may be forming now because there's no plow pan, because it wasn't really farmed. And so we have relatively soft sediments. We also probably have some new unconsolidated sediments from sediments delivered to that area. And I was out there a few years ago doing some vegetation surveys, and there are some areas where I was sinking up to my knees and even up to my waist in sediment. And I think those are like old ponds that have filled in with sediment, still unconsolidated. Wiley Slough, large ponds were a surprise, unclear why they didn't drain well, but they're slowly drying out, either because of improved drainage or sediment deposition or both. While they provide large rearing for small fish and waterfowl, they did inhibit vegetation development. And the vegetation, of course, is an important part of the food chain for both fish and waterfowl. Milltown Island, beaver can colonize restoration sites extensively. Restoring tidal shrub and forest communities requires intervention. That's still something that needs to be done out there. Exploding tidal channels can be hit or miss, requires better planning, quantifying over marsh distances, for example, some more modeling. Fisher Slough, I didn't talk much about that, Eric did. Fisher Slough is really interesting in that there's kind of a novel wetland vegetation community out there There's abundant wapato, burr reed, Plymouth soft-stemmed bulrush, and several spike rushes, which we don't see in the estuarine marsh community. And that's probably because Fisher Slough is kind of along the upper landward limit of what we might consider an estuarine marsh community. It's also kind of, because of the floodgate there and its operation, it might be a little more lake-like or pond-like than estuarine. There's kind of a mix of both there, I think. But it's potentially also a missing community type that was historically more common. We don't really know because we don't have records of what, that habitat type has been lost, basically. But it might have been a more common community type. There's lots of waterfowl out on the Fisher Slough side as well as juvenile salmon. And then the Swimming Channel fill removal sites, we had one of our small sites there, they're basically removing fill, so you remove it on the small areas. And so our minimum estimate of what's the minimum size that a site could still support a blind tidal channel has been kind of supported. So that was nice, especially with Rainbow Marsh. It was like a 3.25 acre site. And it was kind of the lower limit of what I thought we could potentially get away with having a tidal channel actually persist on that site. And in fact, that's what we see. And the other thing we've learned there is that sediment supply on Smoosh Channel can keep up sea level rise. There's dramatic rates of sediment accretion on some of our fill removal sites. And even in a site that's relatively distant from sediment supply, it doesn't get direct sediment supply from the river. It has kind of a convoluted flow path. But in spite of that, because there's such a large amount of sediment from the river, it's supporting persistence of restoration sites along the Swin Channel. So we need further development of predictive models to evaluate restoration success and failure and to improve designs, because predictions provide us with logical expectations that can provide benchmarks or standards or against which we can compare project outcomes and assess restoration of natural processes. There's certainly scope for further refinement of the models and for creative application of the models to planning, design, and monitoring and effective management. So some of the models that I'll be working on in the future: overmarsh flow distance model I mentioned earlier, cross-sectional geometry scaling as a further refinement of the allometry issues, then applying allometry at smaller scales to within channel habitat issues, predictive vegetation models, those need more refinement, and then doing some more predictive modeling about beaver dams, and can we incorporate beavers to a greater degree than we have been in habitat restoration in the estuary. And that's it. Thank you very much.
Any questions for anyone? Eric, Greg, David? I think Amber had to go.
I've got a question.
Okay, Gary and then Jenna.
Yeah, the question has to do with how the observations of the North Fork account for the sediment flow and the succession vegetation that's taken place from, I'll just say, because I've observed it from 1975 to 2020, 21, what I would see is a roughly 1,000 acres increase in scrub shrub habitat that has occurred, and I don't see that accounted for in the report.
Sounds like a question for Greg.
Yeah, there has been marsh development in the North Fork. You can go back to the 1937 aerial photographs and see that there has been a lot of progradation occurring in the North Fork. But the rate of progradation, if you look at the rate of progradation you're looking at the historical photographs, 37, 56, 65, there's some photos in the 70s, like 78, and the 90s, and of course the modern photos. And you look at the rate of progradation, that is of new marsh development over that time, it has been declining. So that rate is declining almost in a linear fashion, very steadily over that time. And in fact, it's approaching zero. Now, the new avulsion in the North Fork has kind of changed that a little bit because there's been, a sudden replumbing of the North Fork, and that's changed the way sediment's delivered there. So that I would expect, I haven't done the analysis yet, but I would expect that if we look at another time period from the last one to the current one, we would see a sudden jump in the amount of in the progradation rate. But I would also expect that progradation rate would eventually slow down again, just as it had in the past. And I think in part there's just but there's kind of a tension between sediment delivery and the process of sediment delivery and sediment removal, which occurs as a result, for example, of wave attack. And so there's a seaward limit to how much marsh we were likely to get just because of wave attack that takes the sediment away. So that's one issue. The other issue, of course, is sea level rise. And so we're going to be battling that as well over time. Now, in the South Fork, there has also been a steady erosion of the marsh, or a steady decrease in the progradation rate. That's not the same as steady erosion. There's been a lot of progradation also going back, you'll look at the historical photos, same as in the North Fork, but the rate there has been much slower, probably because there's a lot more flow going down the North Fork. But the rate's been much slower, and it's been declining also in a linear fashion, just as steadily as in the North Fork. But it's gotten to below zero. So in other words, we're having erosion, net erosion in the South Fork. We're starting to get that in the most recent time periods. And of course, in the Bayfront, we've been getting a declining progradation rate there until the 70s, where it becomes negative again. We have steady erosion in the Bayfront. That's because of sediment starvation there. So I would say all that is to say that we shouldn't be hoping for marsh progradation to bail us out. That's not going to happen. We need to do restoration to recover juvenile salmon, or to recover Chinook salmon more generally. And with sea level rise increasing, that need is probably just going to become more and more pressing.
Can I make a quick comment?
Sure.
Greg, you forgot you did update that analysis at the beginning of the year. I could show the figure, but basically the North Fork progradation rate, as Greg said, has been declining, but it still was positive through the just prior to the avulsion. So it was growing, and the observation that you have of seeing new habitat, including scrub shrub habitat, that's because it was still prograding. Whereas the Bayfront and the South Fork around, for the Bayfront around 1980 and for the South Fork around 2000, progradation rates became negative, and so there was erosion. So there's that net erosion. And at the same time, the avulsion happened in the North Fork, and now there's a big bump just in response to the avulsion of that downstream of the avulsion habitat filling in and becoming marsh and blind channel and other vegetated wetlands too. So, but that's a sort of a temporary bump in the long-term trend of progradation. So, but you're right, the North Fork has been positive, but it's on a trajectory of long-term decline. And that's in our IMW report. I can send that. Or I can show
that'd be good.
We have a figure. There's a figure. It's explained in there.
If you have that online, you can just pop the link in the chat. Would be helpful.
Michael,
just ask Gary. If you want to write your observations down, having been there for so long, and give us a little time to kind of look and think about that as well, and then give you access to these newer reports and come back and chat a little bit more about those observations.
Well, in 2000, Philip Williams and Associates for the Watershed Council did a major study in which they observed a substantial, meaning roughly this 1,000 acres of increased vegetated habitat, which had been basically just tide flats. And they acknowledged that. And for that to have gone away, it would be very difficult for me to believe, having just regularly looked at that area from the upland. And we used to go around all this in canoes and places where there definitely is a change, a very substantial change over time.
Yes, I agree with that. There has been for sure a substantial increase in the North Fork Delta since 1937 historical aerial photographs. That's pretty clear. It's just the rate of change is declining, and the future trajectory of the site is concerning. Things change over time, including the extent of habitat, and also the processes are changing over time. And so the future condition of the North Fork is, if we just look at the trend, it's concerning. And I would say that, yeah, there might be, I don't know what the exact numbers are. I'll just, for the sake of argument, say 1,000 acres. Maybe there's that in the North Fork that's since 1937 or whenever. But to focus just on that is to ignore all the habitat was lost, since European settlement. And so, the recovery plan is about restoring what's missing, and it's about, how much more do we need in order to support salmon growth, to support the salmon life cycle, and to support the population. And the current amount of marsh that we have out there, including what's currently in the North Fork, that's not enough.
Great, thank you. Let's make sure others can get in their questions. I have Jenna and then Colin. Or did I lose Colin? Jenna?
Yeah, I have a couple questions, but this maybe just sets the stage for the next meeting.
Okay, that's a good idea.
And so one of them was for Greg, when you were talking about the Fur Island Channel network development, and maybe if we could just have a conversation about the role of sediment in the channel formation and the building of the marsh. And I guess I would want to know, I think DFW had, well, I know they have a drone and they were monitoring sediment at that site. Their set instrumentation out there at that site. And maybe that just rounds out the conversation of how the subsided farmland is being built up with sediment inputs. And I think this kind of mirrors the response that you had given in terms of the fill removal projects. And then, the same question would hold true for these subsided farmland projects. And it would be good, I think, just to round out the conversation, if we could have that sediment piece at the next series, maybe in September.
Yeah, I mean, we haven't been monitoring sediment the way we've been monitoring fish and habitat more generally. So that's a hole in our monitoring effort. There are sets, I think there's 3 of them out there at the Fur Island Farm site, as I recall.
Yep.
And I think DFW are the ones who are monitoring that and collecting the data. I'm not sure, what their latest data are on that. And so I don't know, to what degree sediment is accumulating out there or not.
Okay.
Yeah, I kind of wasn't expecting you to know, but it's a kind of
good.
more general question of, could you crosswalk some of the tidal channel stuff with the set and get a long-term sense of how that site is recovering?
I would need to give it some thought. I don't want to answer your question right now just because I need to think about it a little bit more. I haven't really given it much thought.
Yeah.
Sure. No, I
But
get that.
I think it's an important question. I think it's an important issue. And I think we probably need to make more concerted efforts at monitoring sediment. And there's a problem with sets, is that sets, they take a lot of effort to put in, and they basically only monitor a single point. I mean, they kind of pseudo replicate. They take lots of point measurements at a single point in space, and there's a lot of spatial variation in sediment processes right over a site. Sediment is different near a channel versus far from a channel. It's probably different seaward than it is landward. So there's a spatial complexity that sets sometimes don't capture.
No, I get that, and I think that was the purpose of the drone, as a double system.
Yeah,
But since I left DFW, I've sort of lost track of it. But I think it's important to round out the conversation.
Yeah.
I
agree. It's an important issue for sure.
And then I had a question for probably Dave price, but since I was running late, I'll apologize. But I was wondering if at the next setup, we could just have a more comprehensive update of the Chinook recovery plan in terms of the escapement goal, some of the productivity goals. And I think somebody had asked that question sort of partially, but Eric didn't have the numbers handy. Could we have that conversation in September? Which would be a bigger picture look at all of the elements of the Chinook recovery goal for the Skagit, how we're doing on those other elements.
So what Jen asked was about the smolt to adult rate return rates. And that's different. That's a productivity measure. I don't know those off the top of my head, but I did in the last Science Summit series, the Chinook Plan Explained, I did insert the goals and explain those, and those tables are pasted into that presentation.
Okay.
So if that's what you want, that they're there. And I'm happy to talk through how those goals are. The important thing that people mostly don't know or remember is that goals are often articulated as a point along a stock recruit curve. So it's not, the goal is the curve, not necessarily a single point. So it's complex, I guess, is you have to understand how the curves work.
Gotcha. Okay. I'll go back and look at your presentation and maybe submit some follow-up questions. Thanks, Eric.
Yeah, there you go. There you go. David, did you want to weigh in at all, or?
Yeah, I was just going to add that we can provide, some update from the viability risk assessment and the very forthcoming 5-year status review to help supplement Eric's presentation. I think he's right. You've got to look at productivity and abundance together, and that graph tells a story through time. So that's a really informative graph. If there's an opportunity to throw fresh data into that, I think that would be valuable to see.
Okay. And this is showing we kind of are going to do a little bit of circling to, as we get this stuff out there in the open, and it generates more questions, and we'll come back to some of these, I think. Colin, and then it'll be about, we'll have to think about wrapping up. So go ahead, Colin.
Yeah, hi, thanks. My question is for Greg. I was also really curious about what the balance of kind of the sediment processes and erosional processes that might be involved with the gradual increase or decrease of habitat area in the delta. But really my question is, I think, going to be more specific, kind of twofold. One is that, is there a difference between erosion that is observed in areas of the tidal marshlands that are directly adjacent to infrastructure like levee systems? And my second question would be really focused on the kind of the trajectory that you're talking about in terms of how much restoration will be necessary and how quickly in order to achieve a desired future condition. And you sort of kind of got at this too with climate change, but I'm curious about how sea level rise can be factored into that. I found it interesting that one of your projections or trajectories was for roughly around the year 2100, which is usually one of the planning horizons for sea level rise, and it'd be useful to understand the kind of broader context of how that would result in decrease in habitat as well for future restoration planning.
Marsh persistence in the face of sea level rise is basically a tug of war, like I said, between sediment supply and sediment removal. And so if you have lots of sediment supply, which the Skagit does, then you should be able to win that tug of war. Now there are, of course, it's not that simple. That's like the most simplistic way to think about it, because there are some complexities that make things more challenging. So one of the complexities is that we have levees along the North and South Forks that basically constrain the river to being within the levees. And so when you get floods, which typically carry a lot of sediment, you also have high energy. And so the river is basically a fire hose that is shooting sediment out its mouth at high velocities and with a lot of momentum. And so that sediment gets carried out into Skagit Bay, especially a lot of the fine sediments, right? So basically we've done, what geophysicists say is that we've increased the jet momentum of the river by confining it within levees. So it's like taking a garden hose that normally just dribbles out the end of your hose, but if you pinch it with your finger and thumb, you create a jet. That's what we're doing with the levees. We're increasing the jet momentum of the river. And so we're taking all this wonderful sediment that the river carries, and we're shooting it out past the marshes. So that's one problem. And of course, the other problem is that we've cut off a lot of these distributaries across Fur Island that would deliver, nice, lovely sediment to our bay fringe marshes. And that also, by the way, increases the jet momentum, right? Because we're confining all that water into the North and South Fork distributaries instead of having it spread out amongst a bunch of distributaries. So a lot of the sediment that we do see that near shore, especially like, for example, the mouth of the North Fork, is coarse sediment, it's bedload, it's sand. And so we're seeing some of that sediment occurring and filling in downstream of the new avulsion. And we're actually seeing shrubs colonizing a lot of that new sediment because the sand is well drained. So it's relatively low elevation, but it drains well. And so the flooding stress to vegetation and their roots is not so high. And so we're seeing kind of surprisingly a lot of willows and alders and things like that colonizing these new sandbanks. So, on that kind of large scale, the delta is at risk and one way in which we could reduce that risk is by reducing the jet momentum of the river. So we could restore the tributaries across Fur Island. That would be one way. That would deliver sediment and fish and water and fresh water directly to the bay fringe and marshes. That'd be all wonderful things. It would also reduce the jet momentum in the North Fork and probably the South Fork rivers as well, but mostly the North Fork. Another thing we could do to reduce the jet momentum is to pull the levees back. And that would give the river during flood times, it would reduce the river energy because it would spill over its banks into the setback marshes now along the length of the North and South Forks. And that would retain more sediment in near the marshes and help them survive sea level rise to a much greater degree. So I think that answers hopefully your big picture question.
Yeah.
I think you had some smaller picture questions about like areas next to dikes, and I really haven't looked into those very much. I do know that there are occasionally borrow ditches outside of dikes. Often they're inside them, sort of landward, but there are some seaward. And I've seen, if you look at photos over time, those seaward borrow ditches can fill in with sediment. And so, and they're probably fine sediments would be my guess. I have walked in some of those sometimes, and they're pretty soft and kind of treacherous. So I'm not sure if that answers your fine scale near the dike question or not, because I really haven't looked more.
Yeah, I guess it was more of like, in some of the images that you showed, it looked like some of that marsh was being lost, concentrated directly adjacent to levee systems. And so, it's sort of kind of gets at the coastal squeeze concept, I suppose, where
the marsh is being lost along the bay fringe, for example, is not directly adjacent to the dike. It's seaward of the dikes. It's the lower elevation marsh. And in fact, what we see along the bay fringe is adjacent to the dike, we have relatively high elevation marsh. And then we have what I call a marsh cliff. It's only a cliff in marsh senses. It's only like about 0.5 meter high. But those cliffs or scarps are a clear sign of erosion. I mean, this is classic. It's been documented all in marshes all over the world, where you get this cliff, 0.5 meter high cliff or so. That's a clear sign of erosion. And what you have below the cliff in most systems, like in England or other places, those are bare areas now below the cliff. But in our system, it's not entirely bare. It has Chenoplectus pungens there instead at low density. And so, but what you see, we also have these what I call marsh pedestals. They're like remnants, they're like haystacks that you see on the outer coast. They're just marsh haystacks. and they have Carrick's lingby on top of them, for example, or other higher elevation marsh vegetation. Whereas at their base, all around them, they have the Chenoplectus pungens. So these are also clear evidence of a historical marsh platform that has been eroded away. And that's well seaward of the dikes.
Got it.
Not well seaward, but clearly seaward of the dikes.
Thanks,
Not
Greg.
adjacent to them.